Okay. First of all, thanks a lot for the invitation. I'm very happy to be able to speak here about my research. This is joint work with Leon Loveridge and Titouan Carrett. And it's work in progress, so the purpose of this talk is primarily to make sense of the title, what I mean by relational and quantum and relativistic things, theories. And then towards the end, if I have enough time, I will try to communicate the latest developments. So let me begin with some sort of motivation. So far, well, except the foundational research like the kind was described in the previous talk and this kind of things. Shall I do? Oh, yeah. So we base our fundamental theories on the framework of quantum field theory, usually, and this is not fully satisfactory in my opinion, and I think it is shared in a larger group. So these are some reasons for which this is not, well, good enough, at least in the current form. So far we don't have any rigorous formalization of interacting quantum field theories. And these are those that we care about in experiments. This framework is tied to the notion of a fixed background spacetime, which doesn't seem compatible with the modern ways of thinking about gravity. And operationality and relationality are, well, in my view, they are compromised in this way of thinking, and I will speak a lot about, well, not a lot, a little bit about what I mean by operationality and relationality as we go. But, yeah, okay. So the goal of this research program, the way I see it, is to try to fix this by developing a new kind of framework, like forgetting quantum fields and maybe space-time as well, and try to take the core things from relativity and quantum theory and try to merge them together in a different sort of way. So the goal would be a framework that is operational, which means basically that I want the things that are going to be subject to experiment to be right there in the framework, so that the procedure of deriving predictions from the formalism should be as straightforward as possible. I want it to be rigorous, non-perturbative. I don't want to introduce any sort of background. I want it to be relativistically invariant for compatibility with special relativity. And the way interactions should be implemented in a relational framework, they should always relate to pairs of systems. That's, well, that's my opinion. That's a program I want to pursue. And yeah, I mean, this may sound too much, maybe a bit crazy, but I like to have dreams. And so the purpose of this talk is to show you what kind of progress we've made with these ideas. They obviously related to some other ideas that are around. So I will try to emphasize where we differ from like other approaches to quantum reference frames. And point, well, I want to make the case that this is not something impossible. Okay, so that's the plan. I will first well, provide a perspective on quantum mechanics that is the relevant one for us, aligned with GPT kind of way of thinking. Then I will define what the notion of a quantum reference frame, what does it mean to have a description of a system relative to a frame, then how it is compatible with what we actually, normally how we describe quantum systems without a reference. So we can externalize the quantum reference frames and recover the standard description of physical systems in terms of single Hilbert space, non-relational degrees of freedom. Then the latest development that was done last year and was the subject of my thesis were frame transformations. So we can, after all these things are established, we can consider two frames and we can see how we can describe a system from one perspective and then the other, and we can change between these perspectives. And then at the end, I want to tell a little bit about where this framework can be pushed outside of the quantum theory as we know it. All right. So first, the preliminaries. So the perspective on quantum mechanics is the following. So everything here is infinite dimensional and continuous, which is a distinguishing feature, I think, among similar approaches. So, well, this is basically because I want invariance with respect to the Poincare group, and there are no finite dimensional representations of non-compact groups. So this is supposed to be the basis or a special case of a relational framework. So I need to go there. So states are density operators. Observables are positive operator valued measures. So this is not standard, I think. Well, I think it should, but basically a positive operator valued measure is the most general way to extract the probability distribution out of a quantum state. So it should be thought of as a map that given a state, states are omegas, and this sort of map, I can construct a probability distribution. Sigma is a sample space, F is a collection of subsets, the measurable subsets. So I should be able to construct a measure which is a map that for a given subset of the sample space, which can be thought of as a proposition that I can measure, I can assign a probability. So this is just the Born rule, generalized to this setup. Yeah, so I don't have time to talk about this. This is the starting point, so to say. These are the only things that I'm going to use to build my framework. I don't care about like the actual vectors in the Hilbert space and this sort of things. It is supposed to be aligned with the generalist probabilistic theories sort of way of thinking. Is there a clarification needed here, or we can go? Okay, then we go. Another thing, and this is not non-standard. I want to, well, so for physical reasons that I will advertise, we will encounter the situation that actually not all the operators on a given Hilbert space are available for some reasons. For example, I will require them to be invariant, like we've heard before. I want physical observables to be invariant, and not all of the observables will be invariant. So I have a smaller subset, but then I want my states that cannot be distinguished by the available operators. I want to identify them. So what I do in such a situation, like for whatever reason, I have a constraint on the set of operators that I can apply to my states. Then I redefine my state space by putting an equivalence relation. So these are states again. So I want to identify states that I cannot distinguish. So this sort of quotient space is what we call operational state space, because it takes care of the fact that we don't have access to all these things. So this is already a more general thing. So this is a simple procedure. It's very much related to the non-restriction hypothesis that people use. But a striking feature is that it already, I mean, it can be done with preserving all the Banach space structure and all these things. It's a well-behaved procedure, but it brings us already out of ordinary quantum physics, because this is not the space of density operators on a Hilbert space. This is something else. And so this is one of the features, not crucial, so if you haven't seen such things, don't worry. So this means that I can span a space of operators out of my given subset, and it has a predual space which is given by the quotient of the trace class. And the only reason I think this is important but not crucial. So, but the point is that in ordinary quantum theory, you have this sort of duality. So the trace class operators in which the states live, they are the predual space to this von Neumann algebra of all bounded operators. And this sort of duality between states and effects is preserved under taking this sort of quotients, which I think is nice, and it makes it compatible also with this GPT kind of thinking. All right, so that's a technical starting point. And now let's think about physics. So the intuition is that coordinates that we use in physics, they are abstractions of physical systems. And it seems that this was at least one of the ways that Einstein thought about this. So he kept talking about these frames and these rods and clocks with respect to which physical quantities make sense. But so the idea here is very simple but quite radical if you think about it for a bit longer, because so the understanding of what are these classical, the standard coordinate systems is that you actually have a physical system, but then you assume two things. You treat it as classical, which is no surprise in special relativity, but then you also you abstract it out from the description, you idealize it to these sets of coordinates, and this gives rise to the notion of space-time, basically speaking. So the idea is to really go back and not insist on having a background, but only to try to speak about relations between quantum systems, without this picture of embedding them in some sort of background. So that's the intuition behind the reference frames. So, we want to be able to orient them. This is what we do when we apply the Poincare transformation to a reference frame in special relativity. So we want the action of a group on this system, and now it's going to be a quantum system. And we also want some means to be able to describe the orientation. So we also want an observable, a POVM, that's going to measure this orientation. Then we want this relationality principle to be there. So I think it's just a fact of the matter that whenever we measure something, there is some other physical system involved. This is, in a way, is going deeper with the relativity principle. So here the reference frame is being understood as the measuring instrument. So this is the physical thing with respect to which we measure other things. So the observables that are going to be physical, they will be defined on composite systems. They will be gauge invariant, meaning that if I can perform a group transformation, we can think about the Poincare transformation, on both systems, the frame and the system, the observables, they should not depend on this. This we've heard already, a similar thing. And it should also be compatible with the choice of the frame, which I will explain on the next slide. And then on top of this, there is a universality of quantum mechanics. So everything, all the systems are going to be modeled on Hilbert spaces. And this is actually one thing that could be dropped from the framework. So for now, we talk about quantum mechanics and quantum reference frames. But I'm deeply convinced that, this is work in progress, but now I'm really convinced that this can be pushed beyond that in more general probabilistic theories. So here's a definition. A quantum reference frame, it's a quantum system. There is a group, G, acting on all the systems, the same group. And now a reference frame is a Hilbert space with a group action, unitary, weakly continuous, and then this frame observable, so a quantum observable, a POVM, that's going to measure the orientation. And we require this observable to have this covariance property, so that it means that it's, it's just compatible with the group action. So we have a group action on the group itself, and we have group action on the quantum system. And this equation here means that this POVM is going to intertwine the action. So it's compatible. And to really advertise this, I would need to go and give you some examples, but I don't have the time to do this here. So you should maybe for now, just believe me that this is a reasonable thing to do. So and it's also compatible with other definitions of quantum reference frames that people give in terms of coherent state systems. So yes, but let me not go to there. Our definition is the following. A quantum reference frame is a quantum system with an action of a group, and a frame observable, which is a covariant POVM. And this is it can be understood as specifying which quantum system is going to be used for your observations and how it's going to be used. What kind of things you will be measuring with this thing. And now I promise to make sense of some sort of relationality, what kind of quantities are relative to other quantities, how to speak about observables on pairs of systems in a meaningful way. So after I've chosen my frame, I restrict the set of available effects that I can evaluate on the frame. So the way to make it formally, make sense of it formally, we can just restrict, we can define such a set, and then say that everything is going to be defined with respect, we can do this operational quotienting with respect to this set. But we also want these observables that are physical to be invariant. So this last set here is just means that they have to. We need this invariance on the composite systems. So the story, the intuition is that the physical things lie in the intersection of these two sets, the physical effects, physical operators. So after I've chosen a frame, I have to take care of this choice. So I cannot now consider operators on the frame that are not my effects, the chosen effects, but I also want the observables to be invariant. And then comes the question if this is possible, because it doesn't seem clear that there are such things. And then comes Leon with his construction. It's the relativization map. So it is a way of generating these things, the observables that are both invariant and framed, so aligned with this choice. So how does it work? For any operator on the system, I can, I need to define what this integral means, but Leon did this, and you can check that it's invariant by just simply changing variables in the integral, if the integral makes sense, but it does. And then it is framed almost by definition, but you can also check and make sure that it's true. So there is a way, and it's called the relativization map, of generating the physical quantities upon the choice of the reference frame that are observables on the composite system, and they satisfy both these principles. So this map is understood as incorporating the actual reference system that normally is being left out of the description into the description. So we define now a relative description to be given on the composite system by this relativized observables. So we understand them as being the physical things, the physically accessible observables. And then we can do the quotienting. So this works on the level of composite system, so I can do this quotient. And also I can represent them equivalently as states on the actual system. But this is maybe I will skip unless you ask me later on. So that's the setup. This is how we think it's reasonable to think about relational quantities. But now I've thrown at you a lot of things that are maybe not fully justified. So what I'm going to do next is try to convince you that this is compatible with physics as we know it. So we can get rid of this reference and recover the usual thing. So now, we have this map. It's called the restriction map, so for any state of the reference, I have a map from the space of observables of bounded operators on the composite system to the operators on the system, and it is just being done by extending this simple procedure of applying the chosen state on the frame and then leaving the system as it is. And this is understood as conditioning the relative description upon the choice of a reference state. The intuition is that the instruments that we use in labs, they are quantum systems, but they are prepared in states that make them look classical, and we just get rid of them. And the theorem that is maybe not very difficult, but it's very important, conceptually speaking, is the following. So I take an operator on the system. So this is what I normally have access to in ordinary non-relational quantum physics. Then I apply the Yen map, the relativization map, and this is the corresponding observable that's relational in our terminology. But then, if I know that my frame has been prepared in a state that's highly localized, then in a limiting sense, I can represent it as the same operator that I would normally care about. Does that make sense? So by externalizing good frames, the frames that admit such sequences of states, I can recover the standard prediction, the standard framework of quantum mechanics. So yeah, under the assumption that the frames that I'm using in the lab have this property, which seems very reasonable, I can go back and do stuff like I normally do. Which means that what we're proposing is not incompatible with well, what we know. So yes, this non-relational framework is recovered in a limiting sense. Okay, now the frame changes, the frame change maps, frame transformations. The setup is the internal frame, so we have a big Hilbert space, and now we decompose it, and two of these systems are going to serve as quantum reference frames. So we have a frame 1 and frame 2. And we've been able to define this transformation that is compatible with having a global state. So this map here to the left, it gives a state that is relative to the first frame, and the map on the right gives a state that's relative to the second frame. And there is a way to map from one thing to the other. And to make it invertible, we need to put another equivalence relation, which basically means that the frame observable of the second frame here has to already be acknowledged by the states in here. This requires much more explanation, I think, but this is how much time I have. So let me just mention some of the directions, and then if you're interested in some specific, well, in one of them more than others, then I can maybe say a little bit in the question part. So I think more general frames and systems can be considered. So we should be able to speak about GPT kind of systems in this language, and also frames. Here, they're the sample spaces of the frames. They're just the group. And I think we should consider also more general sample spaces on which the group acts, maybe transitively. We should be able to speak about interactions between things in the relational way. And I also think it would be very nice to have a categorical implementation of this. So speak about process theories as like symmetric monoidal categories, and define the relational structure on such a thing by mimicking the relativization construction that's here. And all these things, they're work in progress, and this progress is surprisingly fast, I would say. So I'm happy to share these things. Yeah, thank you for your attention.